Hello, thank you for attending my presentation that is entitled Physico-mechanical characterization of gypsum rock for underground quarry stability assessment. The aim of this study is to propose a mechanical characterization of gypsum rock, trying to consider all the parameters that may affect the stability of underground excavation. Gypsum is indeed a raw material often exploited for the production of cements by both open pit and underground quarries, and this requires a specific attention for the characterization, the mechanical characterization for the to evaluate the stability of the, especially on the underground quarry sites. Since gypsum is a natural material, it may present some heterogeneous features even within a single facies that may complicate the mechanical characterization. In addition, in the underground quarry sites, we often see the presence of water or elevated humidity condition, and this presence of water, in particular if joined to the time factor, may induce an additional worsening of the mechanical strength, of the mechanical properties of the material. In order to investigate this topic, I will propose a presentation that will include an introduction, in which I propose some state-of-art of the knowledge about the gypsum properties, physico-chemical properties and mechanical properties. And then I will go a little more in detail to describe the geological, geotechnical and hydrogeological framework of the tested material that we choose to investigate this topic. I will then propose a characterization of the material in terms of physico-chemical properties, and go then a little bit more in detail in the presenting the results of the experimental analysis of about the mechanical response of this tested material. I will then conclude with some consideration on the scale effect and some general conclusions. So let's move to talk about the state-of-art of the knowledges about gypsum rock. We can start to talk about gypsum as a mineral. We know that gypsum has a crystallographic structure that see the presence of a layering that is created by the weak bonds between the hydrogen atoms, and this creates at the scale of the gypsum crystal a mineralogical cleavage along the 010 crystallographic direction. Gypsum has a very high solubility in water, about 100 times the solubility of calcite, as instance, and it has some anisotropic, some mechanical and deformation properties that are anisotropic, and depending on the crystallographic orientation along the 010 direction. Gypsum is present in nature as a constitutive mineral of rocks with a wide range of textural, microstructural and compositional features, and this creates a large heterogeneity in the mechanical response. This suggests the importance of a facies-based mechanical characterization of gypsum rock. In this study, we took in consideration a specific gypsum fashion for these reasons exactly. That is the branching selenite facies, and that is commonly exploited either in open pit underground quarries, and it is present in most of the upper Miocene evaporites of the Mediterranean basin. These facies has a specific relevance for the stratigraphic and ore body reconstructions, because it is associated to a geological key layer. In the scientific literature, a specific mechanical characterization of these gypsum facies is not available, and this is the reason why we decided to focus on, one of the reasons why we decided to focus on these gypsum facies. The scientific literature includes several examples of studies that show the effect of water, the worsened effect of water on the material properties, physico-chemical properties, and strength, mechanical properties. Going more in detail, a little bit more in detail on the geological, geotechnical, and hydrogeological framework of the material that we considered in this study, we can say that branching selenite facies were deposited during the Messinian salinity crisis, a period where when big volumes of gypsum were deposited all over the Mediterranean basin during the late Miocene. During this period, a large variety of facies were deposited all over the Mediterranean basin, and with big differences in terms of grain size, porosity, and mineralogical composition. More in detail, the material that we tested come from the Monferrato area in northwest of Italy, and we choose two quarry sites, Moncalvo and Cagliano quarries, that are located within the unit so-called primary lower gypsum unity, that consists in three big thick layers of macrocrystalline gypsum in patches massive selenite and one layer of microcrystalline gypsum in patches branching selenite. The exploitation in these quarry sites is nowadays in underground environment and involves the first three layers from the top of the ore body. The excavation is performed with a road header with a room and rib pillars quarry configuration. This quarry scheme implies a stress configuration with principal stresses in vertical direction, acting on the pillars, vertically acting on the pillars. In the quarries that we considered, we can reach a level of stress on the pillars of about 4-5 MPa. From the hydrogeological point of view, both the quarry sites see the presence of karst systems, even if there is a difference, because in Moncalvo quarry, this karst system is more located, more concentrated within the conduits. It is the so-called hydro-connected conduit drainage system. While in Cagliano quarry, the water is more diffuse and saturate the rock in a configuration that is called dispersive karst circulation. This, of course, has an influence on the effect of water on the mechanical strength and the mechanical properties of the rock. So, after this general introduction, we can go a little bit more in detail in the characterization of the material that we performed in this study. Again, we decided to test the branching selenite gypsum. That is a material that has a structure that is periodically repeated at different observation scales. At the macro scale, we see big branches of coarse white gypsum surrounded by layers of finer material. And at the hand sample scale, we see a similar structure, but at a different scale, that consists in nodules of big selenite crystals surrounded by fine-grained laminae. This material, this kind of structure, of course, implies a large heterogeneity of a strong heterogeneity of the rock even in a small area, as we can see in this image that shows some examples and that I ordered from the worst in the left to the best material. In order to characterize this heterogeneity, we decided to divide the samples into two groups, two material classes that we called A-type for the best kind of material and B-type for the worst kind of material. The B-type samples are more yellow, brownish, and the layering of the branching selenite structure is thin and very well evident from the brownish color and from the differential erosion. In the A-type samples, on the other hand, we have a grayish color with a well-compacted appearance, and the branching selenite structure is macroscopically identified only by the difference in grain size. But the question is, can we characterize these two groups, these two material groups, these two members, only also in a more detailed way, or not only it's in this qualitative way, but in some more quantitative way. And so to do this, we try to take in consideration different features of the material, the grain size distribution, the porosity, and the microstructure, and the mineralogical composition. To characterize the grain size distribution, we used a method of image analysis with the optical microscope. To characterize the porosity and the microstructure, we used the SEM and the mercury inclusion porosimeter. To characterize the mineralogical composition, we measured the gypsum percentage and characterized the non-gypsum minerals with the SEM-EDS technique and with the XRPD, X-ray diffraction. The results of this analysis show a clear difference for all the considered parameters between the A-type and the B-type material. In particular, the grain size distribution analysis showed that the A-type material is finer and has a higher concentration of finer material. In terms of porosity and microstructure, again, we see a clear difference because the A-type material have thicker fine layers, mainly composed of equigranular minerals, and the porosity tends to concentrate within these layers, while the B-type material has very fine, thinner fine layers, mainly composed by flat minerals, and as a consequence, the porosity is more diffuse in all the rock. As I said, the porosity was also measured with the mercury intrusion porosimeter, and the resulting curves of pore size distribution were associated to morphological images acquired with the SEM. We can see that the first pore diameter group class between 0.1 and 1 microns is pretty similar in the measure of the two material groups, and corresponds to the finer porosity between the finer material on the, of the rock. In the second pore diameter class, again we see similarity between the two curves, and this pore diameter class can be associated to the opening along the gypsum crystals that is similar in the two material classes. In this other pore diameter interval between 7 and 20 microns, on the other hand, we have a difference between the two material groups, because we only have the record of pores for B-type material, and this size of pores can be associated to the microcracks and larger opening along the boundaries between the grains, suggesting that this is the main feature of the B-type material, the presence of cracks and the enlargement of contact between the pores, between the grains. Eventually, we have the presence of pore with diameter higher than 100 microns, and these again are present in both the material groups. Eventually, in terms of mineralogical composition, we see that the A-type material has in general a composition of a higher composition of gypsum with percentages higher than 90%, while B-type material is usually more poor in gypsum. The XRPD analysis showed the presence in both the material classes of non-gypsum minerals that are mainly calcite, dolomite, quartz, and feldspar, and other sulfate mineral and clay minerals, of course. the SEM-EDS compositional maps allows to describe the collocation of these minerals in the rock structure, and we see the presence of clays and other heterogeneous minerals in the fine grain layers, while the gypsum is mainly located in the bigger crystals, in the bigger nodules. So to summarize, we have a difference between A-type and B-type groups for all the parameters, the considered parameters, and A-type material has a finer grain size, has a lower porosity, has a higher gypsum content. We can now move to talk about the results of the mechanical characterization, the mechanical test that we did on this material, and trying to understand how the material characterization, the physico-chemical parameters that we describe now can influence the mechanical response. We can see in this first graph, in this first result, that the material heterogeneity that we described in terms of porosity, grain size, microstructure, and gypsum content has a clear effect on the compressional wave velocity that we measured for all the set of samples that we tested also with the other techniques, and we see that there is a very big range of results between 500 and 5,000 meters of seconds. This heterogeneity is also evident in terms of material strength, in terms of uniaxial strength. We see in this graph the results of uniaxial test performed on both A-type and B-type materials, and we see that the difference in strength is pretty clear, both in terms of peak strength and in terms of elastic modulus. Going a little bit more in detail, we see that all the three parameters that we described before, the grain size, the porosity, and the gypsum content, has a clear influence on the uniaxial strength. The increase of grain size bring to a decrease in uniaxial strength. The increase of porosity again bring to a decrease in uniaxial strength, while an increase in gypsum content bring to an increase in uniaxial strength. Another interesting element that we can consider, and we can observe how influence the mechanical strength, is the orientation of the material anisotropy. As we said before, the branching selenite has a clear anisotropy that is created by these gypsum nodules and the presence of fine grain lamina, but this kind of anisotropy of layering is may have different orientation in the gypsum quarries, because it follows the orientation of the material structure, the rock structure at the scale of the of a larger scale. So we decided to test the effect of the orientation of this layering on the uniaxial strength, and the results is pretty interesting and show clearly a decrease in uniaxial strength for angles of anisotropy between 20 and 70 degrees, while for lower and higher angles of the anisotropy, it means for horizontal or vertical layering, we have the maximum strengths. Similarly on what described for other kinds of rock. This effect of anisotropy is not only on the peak strength, but also in terms of the shape of the curve, because we see that for horizontal anisotropy, we have a longer post-peak, while for vertical or intermediate angles, we have a sudden breakup of the material before the longer post-peak may be reached. To describe this phenomenon, we described the uniaxial test with deck analysis, with this doing a photographical an analysis of photographical images acquired during the test, and we see the comparison of the free test with vertical, intermediate, horizontal angles. We will see now that for vertical angles, as soon the peak strength is reached, we have the breakup, while for horizontal angles, we have a longer post-peak where the coalescence of the failure is progressively reached until the material then completely collapses, but only at the end of the test. Okay, so summarizing all this data, we can say that the main results of this study include that the fact that the material strength, the strength of this particular kind of rock, gypsum rock, depends on the material heterogeneity and on the layering orientation. What we want to do now to conclude this presentation is to try to contextualize these laboratory results in the framework of a real underground excavation. To do this, we prepared a schematic representation of a gypsum layer in branching selenite facies. We see in this scheme the presence of the big gypsum branches surrounded by the finer material in branching selenite facies. We can imagine the presence of some quarry drift in this gypsum layer in different position. For instance, we see the presence of the hay tunnel that is in a more peripheral zone where the branches of gypsum are smaller and their presence is less important, and we will have therefore a better material. On the other hand, in position B, we will have a different proportion of branches, gypsum branches, with a lower percentage of finer material. In addition to this primary heterogeneity, we can see that in some portion of the earth body, we can have a water-induced weathering of the material that produce an additional worsening of the mechanical properties, as we are creating the conditions of the B-type material that we described before. The last consideration that we can do is that due to this orientation, irregular orientation of the layering at the macro scale, we can have an orientation of the layering that is locally different from the horizontal, again changing the mechanical properties of the material. So the jointed effect of the primary heterogeneity, that means the geological variability, the different proportion of gypsum branches and finer material, the additional effect of water-induced weathering and the presence of a variable orientation of the anisotropy of the layering brings to an heterogeneity in the material strength that has to be taken account to have a correct evaluation of the stability of the quarry sites. Thank you for your attention.